the clunky bit here. So, all right, I'll just introduce us, and you know, I think it's best to start as we mean to go on. Is that all right?
I can edit it out if you want. You know, when we're done, because I have a nice easy way of editing, and I can probably extract just the sound. Now that I think about it, I use this thing called SharpCap. Not SharpCap. Shotcut. Yeah, I have another program called SharpCap. It's called Shotcut. Shortcut. No, Shotcut.
Not short.
Yeah, Shotcut. Not short. Shot. It's Shotcut, as in you take a shot with video or something. A video shot.
Oh, Shotcut.
And you want to make cuts of it. Yeah, Shotcut.
I got it. What's going on? Is this actually recording? It's actually doing a transcript while we're
recording and transcript started.
All right, fine.
Nice.
Okay, hilarious. All right, so I'll just okay. Let's just get on with it. 3, 2, 1. Okay, hello everybody. I'm Joe Sanderson, and I'm joined here by Richard Epp. I'm just smiling because this is our first attempt to record something resembling a podcast, in which we're going to just talk about a general subject. This week is going to be Isaac Newton, and so we're just going to share some of our and Wikipedia's knowledge of great scientists, and probably some of our ignorance as well. So, Richard, start me off with some exciting piece of info about Isaac.
Something about Newton. Yeah, I mean, what I really like about Newton is both the breadth of subjects that he thought about, and the depth. Right, I mean, it's crazy. He did stuff like, obviously, like in stuff like physics, right, like we do in 111, the mechanics, stuff like that. But he also did like in optics. He was like an astronomer. He developed a Newtonian reflector telescope, and and something that and lots of stuff like that, physicsy kind of stuff. But also, my understanding is from papers that were not sort of recently uncovered or whatever, like a sort of some significant chunk of his working life was spent thinking about like things like alchemy, and like predicting the date of the end of the world and stuff like that from looking at the revelations in the Bible and things like that. So he was also a theologian kind of guy, a bit of a nonconformist. There were certain aspects of it that he didn't like. I think the Trinity or something like that. But so he refused to do some things, right?
Yeah. So he was and it was quite difficult in those days because I was looking at, he was the second Lucian professor of mathematics at Cambridge, and I've always one story I've always told my class about him is that he was so amazing and so recognized to be this complete genius above everybody else, that this professor resigned his seat so that Newton could have it, and went off and took holy orders instead, which is a great, when you say it like that, it's just, wow, he must have been so amazing. But in fact, really, everybody who had that position was supposed to take holy orders. And so the guy who was also an Isaac Barrow, who was only 13 years older than Newton, he went off and he had done a lot of mathematical stuff. He worked on calculus, apparently. I'm getting a lot of this from Wikipedia, let's be honest, but he the fact that he gave up that seat wasn't maybe quite as shocking, because he still kind of stayed within the university there, and I think he became the warden of Trinity or something like that. So it wasn't like he just gave up his job. And I do know a physicist who did give up his job and go and take holy orders, and I think at some point we've all felt like that. One way or another, but we're still here. So,
well, I think that science sometimes has that sense of you're a little bit of a monk, sort of, right?
Yeah.
There's certainly a great deal of discipline involved and hard work and so on. I don't know.
Yeah. Well.
I was just going to say that.
Go on.
Oh yes, Newton was super intense. I would think, to be able to have the output that he had in all of these areas.
He never
I was just going to say, that location professor thing at Cambridge. So just a interesting point is that Stephen Hawking had sat in the same chair.
Right, yes. Yes. Did I pronounce it wrong? You said it's slightly different.
I don't know. I thought it was L-U-C, Lucasian or something. Maybe it's Lusasian or.
No, you're absolutely right. I'm reading. You see this? Reading was never my strong. It's not Lucian. You know, I thought it was well, maybe it is Lucian. Hang on. Okay, well, we'll solve that problem and or we'll get English graduate to tell us.
So you know, one thing that I sometimes talk about a little bit with Newton, which is kind of funny, is, you know, so for sure he was basically very mathematical. Like if you look at the Principia and, you know, the influence, like one of the, you know, he wrote this book, the Principia, which is probably the single most influential science book in human history, like huge impact, right?
Right.
And lots of the things in that book have been superseded by like Einstein's ideas, relativity, you know, for space-time and general relativity for gravity and all that kind of stuff. But I think the real lasting impact was that, you know, you really have to that understanding the world like physicists do is really a mathematical. You know, the language of nature is mathematics at a really fundamental level, right? And that was really what he did to influence the subject, and then everyone afterwards sort of worked the same way. It became a very mathematical sort of subject at sort of foundations. But also he was big on experiments, like in optics and stuff like that, right? And so, you know, he had the prism, and he invented the word spectrum for the splitting of light and all that stuff. So he did stuff like that, right? But the funniest thing is there's this thing called the Newton eye poke experiment. Okay, so what he did.
Okay, yeah.
So there's some write-up of it. I don't know if it's in the Principia or somewhere. It's in it. It's maybe a different thing, right? But what he would do is he would like you close your eyes, and then if you gently, poke on the side of your eye, you see on the other side like sort of colors and things coming in, right?
I'm trying it.
So
really
get a poke sight right on the side, sort of, and then you
I don't know if you see it. We should warn students not to try this at home.
Yeah, don't use any sharp objects. Just at first use your finger, right? So I don't know what Newton did, but when you read it, it's kind of like it's pretty like extreme what he was doing with poking his eye, right? So he's a really intense person, is what I get from that, right? Just super focused, and yeah.
Yeah, I don't think he would have. Well, I was going to say I don't think he would have fitted in very well, but he probably would have fitted into the typical physics department, because it's pretty much a desirable character trait to be a kind of what was the expression? Prickly eccentric that somebody used about us. Yes.
Yeah. Oh, actually, that's funny because that eccentric thing. So it turns out that so like I said, my impression is that actually, a significant chunk of his time was spent on alchemy and theology, and that kind of stuff. And so, so apparently they looked at his hair after he was dead, and they found mercury in it. So because he'd be doing all these experiments with alchemy, right? And so I remember the idea of alchemy is you're trying to convert less valuable metals like lead and stuff like that into gold, right? And so lots of people were kind of into it at the time, and apparently Newton was big into it. They would have gotten nowhere because nowadays we know how to do alchemy, but it happens at the nuclear level. Nuclear physicists, particle accelerators, right? We can convert one element into another, that kind of stuff, right? But that's at 1,000,000 times the energy than chemistry, right? So they would never have succeeded, but you could just imagine it, right? Because you're trying to do alchemy, converting metals, and mercury is this awesome metal, right? And so he would have done stuff like that.
Yeah.
Actually, when I was a kid, my mom, she was a nurse, and she would bring home, like, a mercury thermometer would break, right? And then she would bring home mercury, right? And then we would pour it on the kitchen table. And then the kids would sit around poking their finger in the mercury. And isn't this mercury really cool?
Oh, my God. Yeah.
So maybe I'm going to become super eccentric in my old age, right? And
I'm sure that hasn't happened already. Yeah. I thought it was bad enough. I had one of those little, toys, where you have the mercury and you have to get it through the maze kind of thing.
Okay.
And I thought that was, looking back, I actually had one of those things, but I never broke it and poked my finger into the mercury.
The things that we learn as time goes on. Oh, mercury is actually bad for you. You shouldn't actually play with it. Yeah.
Well, I'm sure our childhoods were littered with dangerous situations. I remember when there were X-ray machines in shoe shops.
Right.
It's one of those things where you occasionally think, did I imagine that, or did I actually have my
like a fluoroscope or something like that.
Yeah. As if that was actually going to help, really. Anyway, but getting back to Newton, I mean, it was, of course, I mean, again, though, just to bring things back to kind of, back down to earth a bit, that it was quite typical for scientists at that time to be, very much involved in many different, different things, even like, another famous scientist from the time, not anywhere near as well known, but Robert Hooke. It'll come up later in the course when we look at energy and springs. He also was somebody who had all sorts of wide contributions as well to microscopes and springs and even architecture. He worked with Christopher Wren. And so, and even Christopher Wren, in fact, was an astronomer as well, a famous architect. And he had and Hooke had a famous falling out with Newton, of course, which some people think is the reason why there is no known image of Robert Hooke, because Isaac Newton took. Well, I think he was piqued because. Hooke kind of had some kind of a discussion with Newton about the gravitational relationship to separation, I think, and I think he claimed that he pointed out to Newton that it was this inverse squared law, and I guess Newton was very, very egotistical and didn't like to have any. I mean, I think there's also an element that Hooke was going around claiming a lot of other things as well. But Hooke was a big deal in the Royal. Got to get this right. The Royal Society, was it the Royal Institution? Okay, now I'm getting.
I think it's the Royal Society.
I think it's the Royal Society, right? I think he was the keeper of the experiments at the Royal Society, and he eventually had to make this big climb down and apologize to Newton about this. And then afterwards, Newton became very, very prominent in the Royal Society. So there's this kind of conspiracy theory that he somehow got rid of any of the images of Hooke, because he was quite a vindictive person. He in his later life, he became the head of the Royal Mint, right? And he had to pursue people who were forging coins, and he basically would have their hands cut off. That was one of the.
Ouch.
Yeah, or they. Well, that was a mild penalty. Because the standard penalty in those days for almost anything was death, and so he was pretty much.
He was actually a nice guy. He was
a nice guy. That's why he just did the hand off thing. There's go on.
Sorry, that's really interesting. Sort of this dynamic between Newton and Hooke, and I think it just points out that science is it's a very human endeavor. And there's all kinds of egos get involved and stuff like that, and there's all kinds of fascinating stories. Like if you think about light, I mean the nature of light. So Newton had he did all these things, including in light. And for Newton, everything was just particles moving around in a vacuum, like we do in like 111, like particles moving around, forces and accelerations and masses and things like that. And so he figured, well, light is also, just particles moving around. But then his contemporary Huygens was on the opposite end of the spectrum. He said, waves. He said, no, light is a wave. And there's this, this ether that fills all of space and all that kind of stuff. And so I think there was a lot of debate back and forth. But there wasn't any experimental evidence either way. And so really what won out in the end was Newton, just because he had bigger stature than Huygens. So that basically it was from Newton's time till the 1800, around 1801, that it was all, everyone thought, oh yeah, particle and vacuum. And then
Young, I guess.
Thomas Young, in 1801, did an experiment which showed pretty unequivocally that light is a wave.
Right.
And then Einstein came along later after that and showed that, oh, wait a minute, it's actually a wave and a particle. And so both of them were right. And that's the beauty of relativity. You can merge both of them together. And quantum.
Well, I guess that people been a bit frustrated because we haven't mentioned his laws, which is probably everybody's thinking, tell us something about the laws. What's so great about Newton's laws? That's still his number one achievement, maybe, and discovering gravity, whatever that means.
Right. Well, so in terms of like gravity, I think this is the coolest thing. I mean, you know, there's this maybe apocryphal story about the apple falling on Newton's head, and then he thinks about he invents gravity or whatever. And apparently there's probably some truth. I mean, not that the apple hit his head, but that he was just musing in his garden or whatever and saw an apple fall or whatever and wondered, you know, why doesn't it just go sideways or up? Why does it always go straight down, right? And so one way that could happen is if somehow mysteriously the Earth attracted it. There was a force pulling it down, right? And then Newton was smart enough to realize, well, there would also be a force, you know, the apple pulling up on the Earth, right? But anyways, that idea of the force, whatever, right? Which was different from, I've always just sort of struggled with this, but I think it's different from what everyone thought at the time, because back to Aristotle, there was this idea that, well, rocks fall because they belong on the ground, right? Rocky, so something like that, super vague like that, right? And then so Newton, I think, really did come up with the idea of the force, you know, that you know, the rock would exert on the Earth and vice versa, right? Things exert on each other, right? But then I think the big step was the idea that, you know, sure, we do stuff on the Earth here, throw balls around, and we explain it in terms of forces acting and so on. But Newton was the first person to sort of imagine that, you know, I got a rock and the Earth pulls down on it, exerts this force. If I climb to the top of a mountain, the Earth still pulls down, right? And so he would wonder, well, what if I went higher and higher and higher? And would this mysterious force that the Earth exerts on things, would it reach all the way out to the moon and, like, you know, pull on the moon? And then exert that centripetal force to the center to cause its motion, circular motion or elliptical motion around the Earth, right? So that was a huge leap of imagination. And in fact, there was that super simple thought experiment. All you need, and it's really easy to do. I do this in 175 with the students. You just all Newton knew was that the moon was, how far away was it? 60 Earth radii away, and it takes 27 days to go around. And if you put a bit of thought into that, you can compare the strength that the force of gravity would need to be at the moon. You know, the Earth is pulling on the moon with some there's some acceleration out there, right? Where if you drop some free fall, something, right? Compared to free fall on the Earth. And if you compare those two numbers, it was really in the ratio of 1/60 squared. So 60 Earth radii, 1/60 squared. And so that's how he convinced himself, notwithstanding the hook thing, that's how he came with the 1/r squared, right? And and what's amazing about that thing is, okay, great, you can explain that, but then he extended it to the whole solar system, and said, okay, well, maybe the sun has got this 1/r squared kind of force. You know, it shepherds all the planets, keeps them in their orbits and stuff like that. And then he explained everything, like tides and all that stuff, and the most amazing thing with the Principia, I think it was Airy, you know, Airy discs with optics. That guy, Airy, he commented on the Principia, and he said, you know, the thing that would have delighted its readers most would have been the explanation of the precession of the equinoxes. So the idea is, you know, the Earth spins on some axis and it points to some star in the sky, and it's around Polaris, we call the North Star, right? But because of these tidal forces and stuff with the Earth and the sun and all that, and the Earth is spinning and it's flattened out and all that, he could figure out that the axis of the Earth should move around, the spin axis should point to different stars in the sky, different points in the sky. And this was a mystery that was discovered by, what's his name? Hipparchus. No, not Hipparchus. Hipparchus, I think. Anyways, like ancient Greek. Yeah. And so it was a 2,000-year-old mystery. Why is that happening? Why is the Earth's spin axis moving around in the sky, pointing to different stars? And Newton figured that thing out after 2,000 years, right? Bang. Yeah. He just nailed so many things with that Principia. It was just unbelievable. It was like this super tour de force.
Yeah.
Yeah.
Yeah, I mean, yeah, and it's just so elegant. I love the. I mean, maybe the most. Well, it's difficult to. Yeah, maybe the most counterintuitive thing about the whole force business is the way that he managed to decouple motion from force, because I think that, you know, it's very difficult if you're kind of earthbound to imagine that things move unless there's a force acting on them, right? Because there's so many forces resisting motion on the Earth. But he had this kind of thought experiment that if he got rid of the force between the Earth and the Moon, or the Sun and the Earth, or whatever it was, that the Moon would just carry on moving in a circle. This idea that it had been going around the Earth forever, he just thought of it as being, oh well, it's as if it was just going in a straight line forever, but the Earth has kind of captured it, so it keeps it in its orbit, but it's not.
That's huge.
Yeah.
I think that was the thing that, the great, because before that time, I mean, people had this idea that, you need to apply a force to something to make it move.
Yeah.
Right. And the more force you apply, the faster it goes. Right. Yeah. Way back to Aristotle. Right. And so I think that all of the early astronomers, well, actually started with Kepler, was the first one who tried to apply, physics to explain what's going on out there in the heavens. Right. And so he had clearly in his mind that, there's got to be a force that pushes the moon, from the side to make it go around and around, right?
Yeah.
And so then he even went as far as to sort of make something up, like we know the Earth has this magnetic field, right? And so maybe the sun is a magnetic field, and maybe the sun is spinning, and this magnetic field is like spokes of a wheel that's pushing the planets around in their circular orbits, right? A force proportional to their velocity, right? And it was really Newton who broke us from that for the first time, right? In a significant way. No. The force has got to be in the direction of the change in the velocity, like towards the center of the circle. And so then hits the idea, well, what's towards the center of the moon's circular orbit? Oh, the Earth. The force is going to be coming from the Earth, maybe. And maybe it's that same force that's pulling that apple down, kind of thing, right? That was a huge thing. And then what I find sort of amazing then is that was, I think, this huge shift. I think it's probably one of the most important thought experiments in human history, in scientific history. Right, where he suddenly realized that the laws that apply here on the Earth, whatever gravity is doing to an apple, it's the same thing that it's doing to the moon, right? And so then the stuff that happens here on the Earth, we can sort of understand that, and it also remarkably applies to stuff in the heavens. So prior to that time, there was this huge separation between heaven and earth, right?
Yeah.
The lowly earth, dirty earth, stuff happens here, but out in the pristine heavens, it's all different, right? Yeah. But Newton sort of showed that that's not the case. It's all the same everywhere. And so he opened up the entire universe to science, to thinking about it sort of rationally and doing experiments and all that stuff, right? So that's a big impact that Newton had.
Yeah. So this hopefully we've given the listeners an idea of why we thought it was so important to talk about Newton. Although of course, there's going to be other scientists contributing, and we've already talked about Galileo a little tiny bit, but he's Newton's overwhelmingly the dominant scientist that's contributed to this course, really, isn't he? So and as you've said, like he contributed to so many elements of physics. Unfortunately, he didn't do much as useful stuff with the alchemy, but although I suppose some people say that was kind of a chemistry, proto-chemistry, the stuff that they were doing there, because there was not really any, chemistry science. Maybe if there's any chemists that might disagree with that, but
Yeah, actually, that's probably right. I haven't really thought about that or don't know anything about that, but I guess that's probably right. Alchemy was the precursor to chemistry. I don't know.
Yeah, I think so. Okay, well, all right. Well, that was great chatting with you about that. I think maybe we should wrap up and let the students get back to their trying to understand and apply these laws in their assignments this week. So thanks a lot, Richard. Let's have a chat again later in the course. Try it.
Thanks a lot, Joe. I look forward to it.